This is Geometry, Unit 5, Day 1, talking about properties of parallelograms. First thing we want to do is define what a parallelogram is. If a quadrilateral is a parallelogram, then it has two sets of parallel sides. That's the definition of a parallelogram. If we know we have a parallelogram, then we're going to have two sets of parallel sides. This little figure here is an example of a parallelogram. It can be many different, you might even call it different shapes. But notice that it always has four sides. Okay, so it's always a quadrilateral. The angles might be different, but as we change the angles, the opposite sides are staying parallel to each other. So that's what makes it a parallelogram, two sets of opposite sides that are parallel. Now we have some other properties. If a quadrilateral is a parallelogram, if we have two sets of parallel sides, then opposite sides are going to be congruent. The sides opposite have to be the same length. That's what we have going on here. We have opposite sides that are the same length. And every time we move it, we see that they are staying parallel to each other. If we make a quick change, we now see that we have different side lengths. This one's a little bit longer. And that's going to make these orange ones not parallel to each other. It's possible that these two are parallel, but if you notice, these are coming closer and closer to each other as they head further. So those lines are not parallel to each other. It's possible to have one set parallel and not a second set. We would call that a trapezoid. That is not a parallelogram. A parallelogram needs two sets of parallel sides. And what's going to happen with that is we're going to have opposite sides that are also congruent. So RS, segment RS is going to be congruent to segment QP. Segment QR is going to be congruent to segment PS. So that's one of the properties of a parallelogram, that opposite sides are going to be congruent.
I'm confused on why the Q. Like, why is it? Oh,
So another property that we have is if we have a parallelogram, which typically we draw a parallelogram something like that. And if we have an arrow, one set of arrow reminds us that those two sides are parallel to each other. And if we have two sets of arrows, then those sides are parallel to each other. So that tells us that we have a parallelogram. Let's pretend for a moment that this angle here is 110 degrees. Just made it up. We'll pretend it's 110 degrees. If that's 110 degrees, can we figure out what this measurement is right there? If we think about our rules of having lines that are parallel, we're going to have consecutive interior angles. If two lines are parallel, then we should be looking for a whole bunch of different types of angles. So if we have this line as our transversal, this is a parallel line, and this is a parallel line. Some people might say we have alternate interior angles, but this angle that's alternate interior isn't in the shape. Corresponding, this angle down here isn't inside the parallelogram. So we're not going to talk about that one. The only two that we can talk about are those that are inside the shape, and that would be consecutive interior angles. We know that consecutive interior angles are supplementary, so this needs to be 70 degrees. Consecutive interior angles are supplementary if two lines are parallel. Here's another set that are parallel to each other. And if you put in your transversal, your line that goes in between them, if two lines are parallel, you look for one of these types of angles. The only type that we have that's inside of our parallelogram are the consecutive interior type. And those are going to be supplementary. So that's going to make this 110. Which supplementary consecutive interior angles is going to make this 70? And notice, 180 again. So that is one property. Consecutive angles are always going to be supplementary inside of a parallelogram. Do you notice another property that's happening here? When you look at those angle numbers, you notice that one after another adds up to 180. These two add up to 180. 70 and 110 add up to 180. And you keep walking around the shape, and you keep adding up to 180. Do you see another pattern that's happening between these angles? So one thing we notice is that the opposite angles are always going to be congruent. That would be true no matter what your measurements were. If that was 120, this would be 60. And if this was 60, this would be 120. So 120 and 120 would match. If that was 100, this would be 80. If this was 80, this would be 100. 100s would match. So that's our other property we have here. If a quadrilateral is a parallelogram, then opposite angles are congruent. So angle P is going to be congruent to angle R. And angle Q is going to be congruent to angle S. That is true about every parallelogram. So far, we have three different properties we're talking about. We have the property that if we have a parallelogram, then we know the opposite sides are parallel. We know that the opposite sides are congruent. And we know that the opposite angles are congruent. We also talked about one that said the consecutive angles are supplementary. We'll hit that again here in a second. So let's come over here and talk about how we're going to calculate for these variables. Which of those if-then statements are we going to use to help us solve for a variable? So if we're going to solve for the y variable, I notice that these angles are on opposite sides. They're not consecutive. They're not next to each other. They're on opposite corners of our parallelogram. So if a quadrilateral is a parallelogram, then opposite angles are congruent. So what that tells me is that angle F is going to be congruent to angle H, which is going to make 68 the same as angle Y. So Y has to be 68 because opposite angles are congruent. Now we're going to use a different if-then statement to help us calculate for x. What is the if-then statement we're going to use to solve for x? We look up here and we see our three different if-then statements. Which one of those if-then statements is going to help us calculate for x? So we notice that x is part of this side. X plus 6 is part of the side. Well, we have an if-then statement right up here. If a quadrilateral is a parallelogram, then its opposite sides are congruent. Well, we know this is a parallelogram. It has the arrows to show us that. Two pairs of angles, or two pairs of arrows show us that these sides are parallel. Two pairs of arrows show us that these sides are parallel. So, if this is a parallelogram, two sets of parallel sides, then I can say if a quad, that's a little abbreviation, if a quad is a parallelogram, then opposite sides are congruent. Yes, you could say opposite sides are parallel, but that doesn't help us solve for x. So opposite sides are congruent. So x plus 6 is going to equal 13. Minus a 6, minus a 6, x equals 7. So a property we've already talked about so far today, if a quadrilateral is a parallelogram, then it's consecutive angles. The angles one after another. Remember when we came here and you have two parallel lines and you have a transversal, you know that these two angles are going to add up to 180 degrees. Those are considered one of our four types of angles. They are the consecutive interior angles. If you had another parallel line, you have your parallelogram, and it's inside here, and those two angles are part of your parallelogram. Just like X and Y, they are going to be supplementary. They're going to add up to 180 degrees. So we could use that as our fourth if-then statement. So could somebody give us an if-then statement for how we're going to solve for one of the angles? You pick what angle you want to solve for, and you pick your if-then statement that is going to give you the magical skill to solve for it. If we're going to solve for angle Z, we can notice that Z, we don't know what the opposite angle is, but we do recognize that there's a pair of consecutive angles to work with. So if a quad is a parallelogram, then consecutive interior angles are supplementary. So that tells us that Z plus 123, our two consecutive angles, are going to add up to 180 degrees. If we subtract that across, we're going to get 57 degrees. We also know that if we have our parallelogram, then opposite angles are congruent. You could do supplementary again if you wanted to, but it's sometimes quicker to talk about your opposite angles. If you know those are going to be congruent, which are going to make those the same. I was just saving space by not writing that if-then statement, but I'll write this next one just to practice our if-then statements. If a quad, meaning quadrilateral, if a quad is a parallelogram, then opposite sides are congruent. So that means our 2x minus 3 is going to equal 37. So we add the 3 to the other side, and we divide by the 2, and we figure out that x is going to be 20. We come down to our next shape. Our next shape is like a dog gate or a baby gate, and it's more like an accordion. As you pull your two sides in, all of these little parallelograms, they change their shape. So I'm going to draw our parallelogram a little bit bigger so we can really see what's happening. We know that angle DAB, that would be this one up here, would be 65 degrees. And we're looking for the measurement of ADC. We're looking for this one. So if a quad is a parallelogram, and we know that because they tell us that. They tell us that all these are parallelograms. So if we have a parallelogram, or since we have a parallelogram, then consecutive interior angles are supplementary. We are practicing writing out these if-then statements. So I know that my x plus the 65 is going to add up to 180. Subtract that 65 across, and I get 115. So x is going to be 115 degrees. That's using our property about consecutive interior angles of a parallelogram. All right, last one. Last property. Now what we're looking at are the diagonals of a parallelogram. If we take our sticks and connect those together to create our parallelogram, we see in some situations the diagonals might look pretty much the same. But if you start to change it, the opposite sides are still parallel, but now this one doesn't quite reach the full length, and this one is way over. That means the diagonals are different sizes. The diagonals are not the same length. So diagonals do not have to be the same length in a parallelogram, but they do have a fun property. The diagonals are always going to cut each other in half. They are always going to bisect each other. So that makes QM, segment QM, congruent to segment SM. And segment PM congruent to segment RM. So if we look down here at our final situation, the diagonals of a parallelogram, that's what that symbol stands for, is parallelogram. So they're telling us this is a parallelogram, STUV, and it intersects at point W. Find the coordinates of this W. Well, this is kind of silly. We might actually be able to count. But there's a calculation we can do also. We can use the midpoint formula. And that is x1 plus x2 divided by 2, and y1 plus y2 divided by 2. That's your midpoint formula. So when we look at this, we see that S is at 0, 0. We see that point U is over at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 6, 5. So if this is considered our x1, y1, and down here this is called our x2, y2, we would say 0 plus 6 divided by 2 and 0 plus 5 divided by 2. That gives us our W point as 3 comma 5 divided by 2. You could call that 2.5 if you want, but 5 divided by 2, that would be our coordinate. And if we counted it, 1, 2, 3, 1, 2 and a half, that's making sense to what we see in our diagram.